Welcome to this learning video. The topic is about integral calculus. In particular, we will compute the volume and the surface area of a solid of revolution. We start with a sketch now. So let's start with the xy coordinate system. Then a function f is given and it starts at x position A, ends at position B. And now this function is rotated about the x-axis and generates a rotational body. The resulting shape looks like a candle or a roll. Yeah, so you can imagine here discs at the starting and end point. So it looks more like a roll if it is constant. So next, we will consider a very small, infinitesimal small length dx here. And you will see that this is kind of a cylinder. So here you have a disk, shape of a disk, and the height dx generates a cylinder. So this is the height of the cylinder, and the radius of this disk, which we slice out, is f of x. Okay, the next is we compute the volume of the total shape, and it can be computed as a summation, so the integral of these infinitesimal volumes of these cylinders. So infinitesimal volumes summed up. Think of a thin circular slice, like slicing a candle or a roll again. And this resulting disk has thickness dx, and this disk is a cylinder with radius f of x and height dx. This is the key idea behind the disk method, that the shape can be thought as a stack of very thin slices. So, now it's very simple to derive it, because you have base area, which is pi times radius squared, so the f of f squared in this case, times height dx. And the dx is the height of the cylinder. And this is already our formula. You pull out the pi. So the final formula, we integrate from a to b the function f squared dx. So with the help of the infinitesimal approach, the derivation of the formula is straightforward and very quick. Analogously, we can derive the formula for the lateral surface. So the lateral surface is everything but not the disk at the starting point A and not the surface of the disk at the starting point B. So if this is like whatever, a cup, then without the bottom and also without the top. Before we do that, recall the arc length of a function. So it's the integration from a to b of root of 1 plus f derivative squared x dx. You can think of this part as an infinitesimal arc length ds. So actually this means the total arc length of a curve is the summation, so the integral of infinitesimal arc lengths. So how to calculate the surface area now? I call it SA, of a solid of revolution. Think again of the candle. It's now the wax surface, the outer layer that wraps around the shape, and we compute its lateral surface area. So it's the summation, the integral of dSA, so the infinitesimal surface area of such a disk here, of such a cylinder more precisely. So how is it computed? It is now circumference of this cylinder times the arc length instead of the dx, we need to use the arc length. Okay, so these tiny parts here, the arc length is. So the circumference is 2 pi radius, which is f of x in this case, times the arc length. And this arc length, ds, pull out the 2 pi again, you can use for the arc length ds the formula, the root expression from above. Not so simple as before for the volume, but still kind of straightforward. The only difference is instead of dx, you have to use the true arc length here, because it depends on the shape of the function f. You cannot use dx. So if you have another shape, you have more lateral or less lateral surface. So let us discuss this with the next example. We compute the surface area of a sphere. And how can a sphere be described? So again, we have the xy coordinate system here. And what you can imagine is an upper semicircle. So this upper semicircle starts here at r and here it ends up minus r. And when you rotate this, you generate this sphere. So once again, to generate the sphere by rotation, we need to rotate this upper semicircle around the x-axis. That's the only way to sweep out the full surface of a sphere. Yeah, we are not interested in the volume, we want the surface area. So let's begin with the standard equation of a sphere here, which is x squared plus y squared is equal r squared, radius squared. You can express the y component as plus minus the square root of r squared minus x squared. So as the upper semicircle is sufficient, we define our function f we want to rotate as the positive part of these two square roots. So for the formula below, what we as well need is the first derivative. So we compute the first derivative here of the function. Square root derivative is 1 divided by 2 times the root expression, r squared minus x squared. I hope you can still read it, times the inner derivative, which is minus 2 times x. So, and now you plug into the formula for the surface area, which is 2 pi. The limits of integration are from minus r to plus r. Then the function itself is this root expression, and then times, oh, that's a lot now to write here, which is 1 plus the derivative squared. So as you see here, we can cancel the 2 already here to make it a bit simpler. You have to square the derivative, minus squared is plus, so x squared divided by, without the root as you square it, dx. So I need some space here, so I shift the formula below to the left. Next step is here to compute the common denominator, which is then r squared minus x squared plus the x squared here. And what you see, that this is all inside the root, that this r squared minus x squared expression vanishes. And also in the numerator here, minus x squared plus x squared. So this means we get 2 pi integral from minus r to r, and what remains is just the square root of r squared, which is r itself. Radius is positive, so everything is fine. Fine, the radius you can pull to the front, and as there is no x dependency, it's just the length of this integral, which is 2r. So the integral is just times 2r. And we arrive here at 4r squared pi. And this is the well-known formula for the surface area of a sphere, for the area of a sphere. Finally, I want to show you these formulas related to a curve instead of a function f. So again, I draw the xy coordinate system, and now imagine we have a curve here. So for example, this point, this curve point is the vector function xt, and this is now in the plane, so we have xt, yt components, and the parameter t here is running from a to b. So what does it mean? It means that x without the vector symbol is located here, yeah? This is the x position, and here is the x position at the end. So the point itself here is x at A with the vector symbol. And the idea is the same. You rotate it about the x-axis and generate a solid of revolution. And again, you take here infinitesimal arc lengths. So this means from this x at t, you go a little to the future, delta t, and you rotate this disk part here. So I just draw the upper part here and can easily write down the formula for the volume. So how does it look like if you compare to above? You integrate. What is the radius now? It is the y of t component. So the radius squared t instead. But you need to integrate according to t now. You cannot write dx, which is actually here. You cannot write dx. So you need an additional trick. And the trick is the following. The first derivative, so the time derivative of t, you can write as dx dt. And you just express the infinitesimal length dx now as x dot t dt. So please be careful without the vector symbol. This is scalar here. And now you can use this here instead of dx. So you have here x dot t dt. This is the formula for the revolution of a curve, for the volume of revolution of a curve about the x-axis. And for the surface area, it's very similar. So we start at this point. I don't go through all the details once again. So the f of x is the radius, so it's now the y of x. And what we have then is the square root of x dot t plus y dot t dt. So what you can see here at the end is the arc length of a curve formula, which you simply also can look up or check in the previous video. I see there is a tiny typo. I wrote accidentally here y of x. I meant for sure y of t here. And also what I forgot is what are the integration limits. So t is running from a to b for both. So once again, volume is pi times radius squared times this new expression for the infinitesimal dx. And here it is the same with radius, but then you have this infinitesimal arc length formula for curves. So that's all I wanted to tell you. Thank you for your attention and see you next time.